My presentation is on Dysnumeria, the neural processing mechanisms in multi-digit systems. So first, we're going to look at McCloskey's number reading model. He also worked with participants who had number reading impairments, and he proposed a syntactic and lexical class system for word frames for multi-digit systems. So the frames consisted of placeholders that held lexical class information. So you can see that 11 belongs to the teens class, 40 belongs to the tens class. And you can see that errors in number reading seemed to support his model, as the errors were directly related to lexical class within the word frame. His word frame consisted of multiplier words, hundreds, and thousands. We can see a little bit of an example right here, 2041. So 2 would be in the ones lexical class, and in the word frame, the multipliers would include thousands and hundreds. And in the end, we get 2041. Next, we're going to look at the triple code model proposed by Cohen and Dehane, and this model includes quantity representations as well as word frame and visual analysis. So they propose a transcoding mechanism with direct digit to verbal pathways, and these are separate systems and they can be dissociated, as seen in participants with number reading impairments. And so the important focus is the direct route, which includes the visual analyzer, encodes digit string, order, identity, and verbal production, which they propose consists of a syntactic frame. So if we take a look at the proposed verbal production pathway by Dotan and Friedmann, we'll see that the zeros are processed before the number word frame, and the digit independent structural rules will apply before the digit information comes in. So the digit dependent information will provide the number word frame after the structural rules applied, and then the lexical class information will be filled after the building of the number word frame. Here we can see the evolving of these number reading models, starting with McCloskey's model and the quantity representation plus the syntactic lexical word frames. And we have the triple code model, Cohen and Dehane's model with quantity representation, word frames, and visual analysis systems that have direct roots. And next, we're going to see this proposed cognitive model by Dotan and Friedmann that focuses on the direct roots with structural processes and a modified word frame system. For a closer look at this model, we see that an asemantic root is proposed, evolved from the triple code model, and a non-syntactic word frame is introduced. So also distinct processes in the visual analyzer with structural decimal position will be introduced, with number length, triplet structure, and zero detection as 3 distinct subprocesses. And again, we see the linearization process with the digit independent and dependent processes. Prior to articulation, the retrieval of number words, function words, and decimal words will be phonologically retrieved. Let's take a closer look at the visual analyzer system. So this consists of the digit analyzer and the decimal structure separately. Digit analyzer will code for digit order and also digit identity, and the decimal structure will code for number length, zero processing, and triplet parsing. And we're going to take a closer look at this system. The 5 subsystems that are proposed in the visual analyzer system include the digit order encoder, which encodes the values and the order of digits 1 to 9. Deficits in the system include order errors that are seen as transpositions within adjacent digits in the digit string. Digit identity processor is a lexical process, and the lexical identity of the digit is transferred to the buffer and the phonological retriever. So deficits in this would be seen as substitutions of completely unrelated digits in the digit string. The next 3 subsystems of the visual analyzer that are proposed consist of the extraction of structural information from the digit string, which is processed for digit length, parsed into triplets, and zeros are detected and processed in the string. And now this is sent to the verbal production system. The verbal production system consists of 2 separate subsystems. the verbal digit structure processing system, which includes the generation of a verbal number tree. This is digit independent and it's analogous to the syntactic trees of word sentences. The linearizer will make the number word frame, again with digit independent and dependent processes, and the digit binder, which binds the ordered digits onto the number word frame. This is the proposed verbal number tree system, and here's where the structural rules will be applied to build a word frame only based on the structural information from the visual analyzer about the digit string length, the parsed triplets, and the positions of the zeros. What is proposed next is a linearization step where the linearizer adjusts the frame to apply lexical number rules. So tens and ones become teens. Then the digit binder can now bind ordered number digits into the spaces beside the lexical classes. And then we get a complete number word frame here. The number word frame will then be sent to the phonological retriever, which is the last subsystem of the verbal production system. This will retrieve phonological forms of the words, which will include number words, decimal words, and function words. Here, the function words are and, the decimal words are thousand and hundred, and the number words are 4, 7, and 6. So the verbal output we get is 17,406. Deficits in the verbal production system would manifest as errors that include substitution, which is substituting a digit for a completely different digit, where participants would see the number 234 and they would say 294. This would infer an error in the digit binding system. Decimal word structure errors would also be seen with the omission or addition of the word thousand. So 2030 was seen. The verbal output would manifest as 20,000 and 30,000 or 230. This would infer an error in the number word frame. So we're going to get into the tasks now, and we're going to meet our participants. So we have 7 of them. HZ is 24, EY is 34, MA is 26, NL is 24, OZ is our youngest participant, he's 20, ED is 31, and our oldest participant is UN at 79, who has an acquired number processing impairment, while the rest of them have developmental number processing impairments. They're all normal vision or corrected normal vision and right-handed, and HC and EY have letter position dyslexia, and UN, because of the stroke, has acquired aphasia. So in order to control for any alternate strategies being used during the tasks, participants were asked explicitly not to visualize the number for verbal tasks and vice versa, because an impaired visual analyzer can be recruited in number processing even if the visual stimuli isn't being processed. And digits were shown on paper versus computer screens in some tasks because error rates were shown to be higher in computerized tasks, and finger guiding strategies were not permitted. The first task we're going to look at is the sequence identification task for the visual analyzer. So here participants were shown 200 four-digit strings on white paper and were told to circle the ones that were in correct ascending order. Digit strings contained adjacent transpositions and substitutions. So 3, 5, 4, 6 would be in the wrong order. 3, 4, 9, 6 is the wrong order as well. And EY used computer screen for this process. So for this task, transposition errors were shown in 3 participants, in EY, HZ, and OZ, where 3546 was indicated as correct by circling or clicking correct in EY's case, and 3496 substitution was noted as not correct. So transposition errors were shown in the absence of substitution errors. This indicates or infers an impaired digit order encoder and an intact digit identity processor, which is valid for the definition of a classical dissociation. The same decision tasks, testing the same processes, except that participants were asked to circle a pair of 4-digit strings shown on paper when they matched. 36 transpositions were shown, indicating a diff order, and 36 substitutions were shown, indicating a diff identity. The next same diff decision task is measuring for digit length processing. So digit strings consisting of 3 to 6 digits were shown on a computer screen for 1 second with a delay of 500 milliseconds and then shown again. And participants had to make a decision whether they were the same or whether they were diff. These are the same. Diff digit strings consisted of different identities with completely unrelated numbers or different lengths. Errors within the visual analyzer showed selective deficits for digit order and digit number length. In 2 cases for EY and MA, EY showed digit order deficits with spared decimal structure deficits, and MA showed decimal structure deficits with spared digit order deficits. And this qualifies for classical definition of a dissociation. Next, we're going to look at the digit string naming task, testing verbal production and the visual analyzer. So 120 Arabic numbers were shown on white paper, consisting of strings of 3, 4, 5, and 6. 63 of them contained 0. The instructions were read aloud this digit string. So EY read aloud 2,354, a digit order error, and 2,034 with a self-correction was read by NL, which is a decimal shift error. So if we look at the errors in the number reading task for digit strings, we'll see the transpositions where the adjacent digit is in the incorrect order with EY, where she said 2,354, and then we see decimal shift errors, where the order is maintained with the incorrect decimal position. So we see 20, 30, 345, 2034, and the errors were mostly seen in the leftmost digits, and they were proposed to be called first digit shifts, and these were seen in OZ, ED, MA, UN, and NL. In summary, the digit order encoder was impaired for EY because of her transposition errors, and decimal structure was intact. And digit order encoder was intact for 5 of the participants, whereas decimal structure was impaired. This is a valid argument for double dissociation for 2 separate systems for structure and order. And the first digit shift could originate in the verbal production, and this will be tested. So Dotan and Friedmann performed a task that involved multi-digit strings with comma separators, where participants were asked to read aloud 120 pre-parsed digit strings that were parsed for thousands and hundreds. They hypothesized that this should compensate for deficits in the visual analyzer. And what was found was that HC, MA, and ED had decreased error rates that were significant. This finding was consistent with previous tests that indicated that HC, MA, and ED had deficits that originated in the visual analyzer. So it was hypothesized that UN, NL, and OZ had deficits originating in verbal production. Verbal production was tested by a multiply and divide by 10 task, where participants were instructed to do simple multiplication or division by 10. Read the question aloud and then say the response out loud. So 6,500 times 10 would be computed as 65,000, and the verbal output would be 65,000. Deficits in verbal production system would produce a high error rate in this task. So if we go back and look at the participants with first digit shift errors, we can see that the participants who did not gain from the visual analyzer task did have deficits within this verbal production task. So this is consistent with the hypothesis that these 3 participants have deficits within the verbal production system. Another digit string naming task that included zeros and ones was performed to isolate for the zero processing system. So in this task, HZ and EY were shown 350 Arabic numbers that consisted of 4-digit strings with the digit 0. The instructions were to verbally name the digit string. The digit strings without 0, EY incorrectly named them with high digit order errors. However, digit strings that contained the digit 0 contained no digit order errors. So 2305 would have been verbally outputted as 2305, which is correct. The errors in this task provide support for separate systems with digit order encoding and zero processing, where EY had selective deficits for digit order encoding and not zero processing, and HC had both zero processing errors and digit order errors. This provides support that zero processing is manned by a dedicated process, and digit strings with zeros were processed by a separate system for EY, where her errors were spared when digit strings included the digit 0. We can see here Dotan and Friedmann's proposed loci of deficits for each of the 7 participants, with the subsystems within the visual analysis and the subsystems within the verbal production providing selective deficits for each participant, where NL, OZ, and UN had predominant deficits within verbal production, and the rest had predominant deficits within the subsystems of the visual analysis system. Some key findings in this study by Dotan and Friedmann are that multi-digit structure processing has different systems for digit identity and digit structure, where the structure of a word frame can be built independent of digit identity. Also, EY had spared digit order errors in the presence of 0, inferring compensation from this subsystem, which warrants further research. Differentiations can be made now for different types of dysnumeria, where isolating of these specific deficits can help support more specialized therapies for these different types of dysnumeria. Thank you for listening, and here are my references.